Hello, this video is for Module 4 Part 1 and includes an introduction to predictive analytics through the use of a simple linear regression model. Okay, let's go ahead and get started. So, what do we mean by analytics? Analytics is a term that encompasses a wide variety of analyses that can be done with data. There's a particular type of analytics called predictive analytics, and that consists of a collection of techniques that use existing data to make predictions for unknown outcomes. Okay, for our first example here, we're going to consider data from the Big Cities Health Coalition, which was developed by Drexel Urban Health Collaborative. If we go to their website here, you can see that their main purpose here is to explore health issues in urban communities across the country. They do have a very rich data set which can be downloaded here. You simply need to agree to their terms, and then down below you'll be able to download. Go ahead and do that. Here you can download all of the data if you want. As I said, this data is quite large, fairly rich. I have reduced the data down so that we could run some regression models on that, and that data is available here in the Google folder. So let's first look at the relationship between deaths from COVID-19, and this information here is for 2020, so the first kind of when COVID-19 got started. Looking at the relationship between COVID-19 and deaths from pneumonia or influenza. So there's certainly a good understanding of the number of deaths from pneumonia and influenza. We had that for several years here. And these are the numbers for, I think it's 35 different cities across the United States, kind of larger cities across the United States. Now the COVID numbers for 2020 especially were not as well known. There was a lot of errors in the reporting of those, etc. So the goal here is to try to use our pneumonia influenza information to try to make predictions or understand what's happening with the COVID-19 deaths. So a scatterplot is going to be used to investigate the relationship here. My predictor variable, okay, is pneumonia or influenza deaths. That's going to go on the x-axis. My y-axis is called the response variable, and that's the variable you're trying to make predictions for. So this picture here allows me to see the relationship between these two variables. Some observations that I made here regarding that scatter plot is that there's a positive relationship between these variables. So as the death rate from pneumonia goes up, we can see that the death rate for COVID-19 deaths goes up. So there's a positive trend in this plot. This trend also looks fairly linear. So you can imagine a straight line, kind of a straight trend line going through that data. The relationship is said to have a moderate strength. So their points do have some variation in the COVID-19 deaths. So what I'm looking at here is the amount of variation in the up and down direction here. We usually denote the strength of the relationship from weak through strong, and this is kind of in the middle here. Also notice when you're looking at the values here that the COVID-19 deaths are considerably higher than the pneumonia deaths. So the pneumonia and influenza deaths range from about 5 to 25 or so here, but the COVID-19 deaths range from up to near 0 up to about 350. And the units here are number of deaths per 100,000 people, and this information has been adjusted by age. And what that means is it allows us to make fair comparisons across different cities when we use this type of scale here. We don't have to worry about, for example, a city in Florida having much older people than maybe a city like Kansas City or something. So the age adjusted has taken care of that for us. Let's consider some of the observations that I've pointed out here. This dot down here in the lower left corner is for San Francisco. Okay. Here's Phoenix, Arizona is very close to the trend line here. New York City here was very high. So their influenza death rate was about a little bit short of 20, but their COVID-19 death rate was quite high. And again, when COVID hit the United States, it hit New York City pretty early and pretty fast, just because of the high population density. So some of the observations here, some of the cities are below the trend line, like San Francisco, Memphis, Tennessee, okay, and others are above the trend line, like New York City and even Minneapolis. If a city is below the trend line, then a prediction for the COVID-19 deaths based on pneumonia or influenza will be too high. So here, for example, here's the actual COVID-19 death rate. Looks like it's about 10 or so, quite low here for San Francisco. But if we make a prediction using all the data, we would predict that to be about here at about 50 or 60. So our prediction would not be very good for San Francisco. On the other hand, a prediction for Phoenix, Arizona will be very good, because again, we're going to use that trend line to make that prediction, and you can see that the actual rate was right around 100 or so, and that's what the predicted value would be for Phoenix, Arizona. How do we go about making a prediction? Well, we just need the equation of this line. We're going to use software packages to get that for us. So once you have that equation of that line, then I can simply just input a value for a particular city and then into this equation to make a prediction. So for example, if I wanted to predict the COVID-19 death rate for Madison, Wisconsin in 2020, what I would need to do is get their death rate for pneumonia and influenza. Now suppose that value was 14.3. So we would just take that 14.3 and plug it into our equation. And we would predict the death rate for COVID-19 for Madison, Wisconsin to be about 128. Again, that's number of deaths per 100,000 people, and that's age adjusted. Okay, so let's talk a little bit more about some of the details in a simple linear regression analysis. For example, how do we get this equation? What are some of the other quantities that we get or want to understand when we're doing a simple linear regression analysis? So again, we're going to use data from the Big Cities Health website. And I have what I call the Big Cities Health Common Reasons data set. And this has, again, the 35 cities, but I have several different reasons here. You can see diabetes here. And then down below that is deaths due to firearms. We have strokes, etc. The example that we're going to consider here is going to be deaths from suicide. Okay, so down here towards the bottom, there are the deaths for suicide. And what I would like to do is compare the deaths of suicide between the females and males. So I have a female death rate, and I also have a male death rate. So the first thing that I want to do here is take this large data set, okay, which has been reduced down from the original. Okay, so I want to take this data set that I have here and even reduce it down further to include only the suicide death rates. And to do that, I'm going to use an apply and filter action on my data table. So here, for example, is how I would do that in Google Spreadsheets. Again, it's quite common that I'm going to have to manage the data or reduce the data down before I can do modeling. So again, what I want to do here is understand the relationship for female death rate and male death rates And these are deaths due to suicide. And again, for these 35 cities here. These numbers again are number of deaths per 100,000 people, age adjusted. So the first step in doing a regression analysis is creating that scatter plot. I have two different options here for videos. The one on the left shows you how to create a scatter plot in Google Sheets, and the one on the right in Excel. Here is the scatter plot, and I can see that the female death rate here is along the x-axis. That's going to be my predictor variable. And then on the y-axis is going to be the male death rate, and that's considered the response variable. Again, I want to try to predict or understand the male death rates from suicide using information about the female death rates. Quickly, some of the observations here again is that a positive relationship exists between these two. So as the female death rate increases due to suicide, I can expect the male death rate from suicide to increase. Again, the relationship appears to be fairly linear. And also notice, again, that the numbers for the male death rates tend to be somewhat higher than the female death rates. We can edit that graph a little bit. Here what I've done is made the two axes the same. So the male death rates here go from 0 to 40, and then the female death rates go from 0 to 40. I used a drawing tool in a spreadsheet to just add a line where the amount, or the line where the suicide rate would be the same. So here, if the female death rate was 25, then the male death rate would be 25. So what the green line represents here is when the two death rates due to suicide would be the same. Now this data is above that green line that represents them being the same. What that means is that the male death rate is higher than the female death rate. So we can see that the female death rates from suicide range from about 2 or 3 to no more than 15, whereas for males they start out at about 10 and go all the way up to nearly 40. So the death rate from suicide for males is considerably higher than the death rate for females. This plot here is kind of the standard plot that we would use. This other plot that I created here, again, was just to help assist you in understanding the relationship between those two. And it makes sense here to make the axes the same, okay, because these two values, or these two measures, are on the same scales here. Okay, a regression analysis then is used to understand the relationship between the response variable and one or more predictor variables. If I have just one predictor variable that is being considered, then we call that regression model a simple regression model. Whereas if I have more than one predictor variable that's being considered, we consider that, that is said to be a multiple linear regression model. These regression models can be fit in spreadsheets. There's videos here. There's also a very nice online app. It's at stats.blue, that allows you to fit regression models. I was surprised at how well that app works. So there's a video showing you how to do that in the online app. Here's kind of the standard regression output that we get from software packages. Okay, I have grayed out some of the things that I'm not going to discuss here at this time. There's really just 4 quantities that we are going to discuss here, and that is the prediction formula, which is given by the coefficients here, something called the R squared, and then another quantity called the standard error. So those 4 things are going to be talked about here. Let's first talk about getting the prediction formula. So the prediction formula is given by those quantities listed underneath the coefficients. My Y, or my response variable, is predicted male suicide rate. That is equal to the intercept here, so the 4.83, plus the coefficient for the predictor variable. My predictor variable here is the female death rate from suicide. So that equation is, again, 4.83 plus 2.67 times the female death rate. Let's talk a little bit about the slope and y-intercept. Now, it's maybe been a while since you've thought about those things, but we have very practical and useful interpretations of these quantities in the context of this example. So recall that the slope is equal to just the rise over the run. So in this case, the slope is going to be the coefficient that is attached to my predictor variable. So the slope here is 2.67. I can express the slope as 2.67 over 1. So what that means is for each run, okay, so a run here on my scatter plot is going to be movement in the female death rate direction. So for each run, so what I mean by that is suppose that the female death rate goes up by 1, I'm going to expect the rise, which is going to be the increase in male death rates, to be about 2.67. So the slope here, let's go back down here and, okay, so there is a 2.67 unit rise for each 1 unit run. So this implies that there are 2.67 male suicides, okay, for each female suicide. So again, that rate is considerably higher for males. Okay, so again, if I run for each additional suicide death, for a 1 unit increase in my predictor variable, I can expect my response variable to increase by 2.67. Okay, how about the y-intercept? Now, typically the y-intercept is less important or has less interpretation, at least practical interpretation, because the y-intercept would be, so I'm just talking about this 4.83 number now. If the female suicide rate were 0, then this part of the equation would go away, and you'd end up with 4.83. So if the female suicide rate were 0, I would expect the male suicide rate to be about 5, or about 4.83. Now again, I don't think there's any city in the United States that has a female suicide rate of 0. So in a practical sense, that might not be that meaningful. Okay, let's talk a little bit about the quality of the predictions. So an accurate prediction is one for which the predicted value closely matches the actual value. Oftentimes, the way to visualize the accuracy of the predictions is to actually create a scatter plot. Now this one's different than the one above. Here I am plotting the predicted values against the actual values. So these are the predicted values for the response variable. Here on the y-axis are the actual values for the response variable. And again, I have a green line snapped in this plot using the drawing toolbar. The green line is going to indicate where my predictions are very good. So let's pick on that point right there. You can see that the predicted death rate due to suicide is about 25, and the actual death rate is right at about 25. For whatever city that one is right there, the predictions are pretty good. Up here, the predictions aren't as good. The actual is about, what is that, 23 or 24? Excuse me, the predicted is about 23 or 24, but the actual is over 30 here. So whatever city that is, the predictions were not very good. Now the correlation, Pearson's correlation measure in this plot, is one way that we can identify the strength or the quality of our predictions. The correlation measure here is given by multiple R in our regression output, and that value is 0.8933. The more common measure is to simply square that value. So if I take the 0.8933 and square that, I get 0.7980, which is about 80%. Okay, so the higher the correlation value, certainly the higher the R-squared value is going to be. The R-squared value ranges from 0, okay, all the way up through 100%. And the closer you are to 100%, the more accurate the predictions are going to be. There is a more technical interpretation of R-squared. So here I've discussed this as just the square of the correlation measure in this plot. A more technical interpretation in the context of this example is that about 80% of the variation in male death rates due to suicide, so that's my response, male death rates due to suicide, about 80% of the variation in the response can be explained using this linear model and also the predictor that I'm using, which is a female death rate due to suicide. So again, if I can explain 100% of the variation in my response, then I have a really good model. If I can explain 100% of the variation, then all of these dots are going to be right on top of the green line, which again means that the predicted values closely match the actual values. Here I've identified a set of cities on this plot. The one that was off here a ways was Kansas City, Missouri. I highlighted that one above. So for Kansas City, Missouri, I'm going to have an under prediction here, right? So I'm going to predict for Kansas City, Missouri, I'm going to predict it to be about, what is that, about 24 or so? Okay, but the actual is at about 34. Oh, not 32 or so. So I certainly under predicted for Kansas City, Missouri. On the other hand, for Seattle, Washington, I over predicted. How do we go about measuring the prediction error then? So the prediction error is simply how much I missed the actual value by. So the prediction error is simply take the actual response variable and subtract the predicted response. So in order to do this, okay, here I have shown you this in a scatterplot, in a spreadsheet here. So here is the female death rate. Here's the male death rate. That's the actual death rate here. I'm going to use my equation here to get a prediction for the male death rate. Again, I'm going to use 4.83 plus 2.67 times the female death rate, which is right here. That's just for Austin, Texas. I need to do that for all of the cities all the way down. My prediction error, okay, is simply going to be the difference between the actual. So let's talk about Baltimore, Maryland here. The actual is about 15.7. I predicted it to be about 13.4. So if I take 15.7 minus 13.4, I'm going to end up with 2.33. So you can see here that my prediction was an under prediction by about 2.33. This is a little counterintuitive. Even though I have a positive prediction error, what that means is I under predicted for that observation. Here in Boston, Massachusetts, the actual male death rate to suicides is about 10. But if I make a prediction based on the female death rates, I would estimate the death rate due to suicide to be about 12.3. So I over predicted here for Boston, Massachusetts, which is going to end up with a negative prediction error. There's a couple of different ways that we quantify or measure the typical amount of error. And one is based on the mean squared error, or actually the root mean squared error. And the other is based on the absolute error. So I've computed two columns here. Column H is for the squared error, so just taking this quantity and squaring it. And then the column I over here is the absolute error. So you can see that this is negative 2.21 is my prediction error, but I took the absolute value of that and I just got 2.21 there. So this spreadsheet here shows you various predictions and also the calculations for the prediction errors. Then what do we do once we have all of these prediction errors is we attempt to measure what a typical amount of error is. There's two ways of doing that. There's the root mean squared error, which again uses the squared errors. And then we have the mean absolute prediction error, which uses the absolute errors. Now there's a slight variation between these two things. The n-2 here is used in the root mean square error, whereas just n is used in the mean absolute error. And the reason that is because the root mean square error, okay, is a metric that has better statistical properties than the mean absolute prediction error. And one of the ways that it has, or one of the things we have to do to allow it to have better statistical properties is not to divide by n, but to divide by n-2. 2 is the appropriate number to subtract when you have one predictor. There's actually two things that are being estimated in your regression model, and that is the intercept and the slope. So the reason we're using n-2 is because there's two things that are being estimated in your regression model. If I had two predictive variables and then an intercept, I would want to use n-3 here. Generally speaking, we don't have to worry too much about the use of n-2 versus n. For a large data set, you're not going to have much of a difference between these two quantities. Or excuse me, you're not going to have much of a difference here if you use n-2 versus just n. You will see that there are some differences between this measure, root mean square error, and then the mean absolute prediction error. So let's go ahead and calculate these two things for the data that we have here. So the root mean square error, often abbreviated as RMSE, again uses the squared errors, the sum of those. So here I got to come up to my data, my spreadsheet here where I was doing this. I need to sum up, get a total for all of the values in column H. Okay? And then I need to divide that by 35 minus 2, or 33. My root mean square error number is about 3. If we use the mean absolute prediction error, which again is abbreviated MAPE, that is going to use the sum of column I, which is the absolute error column. Again, I need to get the sum of all the values there, which I guess is 78.28, and then I'm going to divide by the number of observations that I have, which is 35. Here you can see that the MAPE measure is about 2.24. In this particular example, the root mean square error is a little bit higher than the MAPE value here, the mean absolute prediction error. That's not always the case that this one will be higher. So one of the reasons that these differ by a little bit is because I only have 35 observations. If I had many more observations, then these two measures would tend to agree with each other a little bit more closely. Now the prediction errors tend to be around 2 or 2.25, or if you were to use root mean square, around 3. But those prediction errors are pretty small considering that the male death rates from suicide tend to be between 15 and 30. So if we look at the y-axis on these plots, okay, the actual, where is it at here? The male death rates, again, tend to be between about, 10, I guess, and 35 or so. So being off by 2 is not too bad. That's a pretty good prediction. Okay, let's talk a little bit about another plot that is often used in understanding how well our model is doing. And that is a plot of the predicted values, again on the x-axis, but on the y-axis here I have the prediction errors. The two quantities that we just talked about, the root mean square error and also the mean absolute prediction error, is simply trying to identify how close these observations are to this horizontal line. This horizontal line here would be when the prediction errors are 0. So here, the average or typical distance from a point to the line is about 3 when I use the root mean square error approach, or it's about 2.25 when I'm using the mean absolute prediction error approach. We want these points to be scrunched down along this prediction error equals 0 line. We've already hinted at this, but points that are above, okay, the points that have a positive prediction error, what that means is the model underpredicted for those observations, whereas points that are below this prediction error equals 0 line are points where we overpredicted. Here we pointed out some of the cities again that I also mentioned up above in that plot. You can see that Louisville, Kentucky has a very small prediction error. Okay, if we go up and look at the plot that we had before, where I identified some of those cities. Where is that at? You can see that Louisville, Kentucky is very close. Okay, the actual prediction, the predicted value, excuse me, and the actual is very close for Louisville, Kentucky. So the prediction error for Louisville, Kentucky is going to be very, very small, and that's what we're seeing here. Whereas Kansas City, Missouri, the prediction error is quite large. We tended to, grossly or substantially underpredict the suicide death rates for males for Kansas City. Just some final thoughts about modeling here. There are, generally speaking, 2 main approaches when we're doing modeling. One is to understand the relationship. So the purpose is to understand exactly what is going on between the response variable and the predictor variable. And then another approach is to just obtain the best possible predictions at all cost. So not really worry about the relationship between those, but just get the best possible predictions. Generally speaking, when we talk about statistical modeling, we are more in the camp of number 1 here, trying to understand the relationship between the variables. Whereas when I'm doing machine learning or even artificial intelligence, generally there, the purpose is just to get the best possible predictions. Now, certainly a regression model can do both of these, okay? But there are better ways or other methods that exist to get the best possible predictions if you don't really care about how the relationship is being built between those, or how it goes about explaining the relationship. Also, we should mention the idea or the notion of cross-validation. So generally speaking, the data used to measure the predictability of a model should not be used to build the model. So cross-validation is a technique in which data is split into 2 parts. One set is called the training set, and another is called the test set. A regression model is built using the training set, and then the outcomes from the model are used to make predictions for the data in the test set. When we use cross-validation, we have a much better idea of the true predictive ability of a model. In this example here, I did not use cross-validation. I used all of the observations, all 35 cities, to build my model. And then I was investigating the predictive ability or the predictive error on those 35 cities. So a better approach might be to take maybe 5 or 8 of the cities and hold them out and put them in what is called the test set. I would build the model using the other cities, so the other 25 or so cities, I would use to build the model, and then I would verify the model or test the model on those 5 to 8 cities that were held out. Again, that's going to help me better measure the true predictive ability of a model. Okay, for the task here, I have 2 scatterplots, one on the left, which has female life expectancy plotted against male life expectancy. So here the predictor variable, again, female life expectancy. The response variable is male life expectancy for these 35 cities again. And then on the right, what I have is, this is genders combined. So lung cancer death rates plotted against life expectancy. And this includes both males and females here. I've given you the predictive formulas for each of those scatter plots, also the R-squared, and I've asked you to look at, I guess, 7 questions here to try to answer. Okay, that does it for this video. Thank you. Have a good day.